I know. I just put away out the.
All right, we're going to jump back down to chapter 19, which deals with redox in chemistry. And one of the biggest applications for redox is electrochemistry. Electrochemistry would be batteries and something called electrolytic cell. So the batteries are discussed in the first part, and electrolytic cells are discussed in the last part of this chapter. Batteries produce electricity by converting chemical potential energy into electrical energy. Electrolytic cells do the opposite. Electrolytic cells convert electrical energy into chemical potential energy. And so electrolysis we use to drive unfavorable reactions. So if we do a reaction direct, we aren't generating any electricity. So these are redox reactions. This is silver nitrate with copper metal. You can see the crystals of silver growing there. What we should do is we should separate those. And that's what we do in battery. So we'll put silver nitrate in one beaker. And in this beaker, we're going to use an inert electrode. That is silver metal would probably be best, because what's going to happen here is the silver ions are going to try to pull the electrons off the silver, but it's not going to be successful. But attached to the silver is a copper electrode, and the silver ions can oxidize copper. And so what's going to happen here is the silver ions will oxidize the copper metal in the other beaker to form copper 2 ions. And this is our battery. We need a salt bridge, though, because if we don't have a salt bridge, then we're not going to generate any voltage. And the voltage that we generate here are 460 millivolts, or 0.46 volts. So the silver pulls the electrons, and in the process, silver ions gain an electron to form silver metal. So we're going to grow silver crystals on silver metal, which is good. And then this electrode is going to be eaten away. And then we have names for these. So talk about the names for these here. So this is the reactive electrode here. And this one is an inert electrode here. It's a reactive electrode because copper is actually a reactant in this redox reaction. We're oxidizing the copper metal itself. This electrode is called the anode. It's called the anode because the anions migrate. And so here's a nitrate that's being pulled over here, because for every copper 2 that's generated, we have no anions. And so for every copper 2, we need 2 nitrates come over here. This electrode here, the inert electrode, this is called the cathode. Is what's happening, we're losing silver ions depositing to form silver metal. These nitrates have no cation, and therefore potassium ions are going to come in here. So for every silver ion, we have 1 potassium ion come in. Actually, for every copper 2 that's generated, we need 2 silver ions, because it's, each one gains 1 electron. And so the overall reaction for this copper solid plus 2 silver ions yields copper 2 plus 2 electrons. And so we're conducting the redox in 2 separate beakers. Over here, what's happening? What's happening is oxidation. Oxidation happens at the anode. Over here, what's happening is reduction. Copper is being oxidized, silver is being reduced, silver ions are being reduced. So reduction is happening here. The electrons are traveling left to right. And so this is the typical way we write a battery. We write the battery on the left. So A, C, alphabetical. And then oxidation, reduction. This is also alphabetical. And so the anode's always written, it doesn't have to be, but it's nice if you write the anode on the left, we have oxidation. And if you write the cathode on the right, reduction. And so over here, we're generating electrons. At the anode, we generate electrons. At the cathode, we consume electrons. And the electrons flow left to right. So we'll try to generate the cells in this way. Each cell will have the half reaction. And so the half reaction that occurs here is the oxidation half reaction. The oxidation half reaction is copper goes to copper 2 plus 2 electrons. And then likewise, in this beaker over here, we're going to have the reduction half reaction. The reduction half reaction is silver ions gain an electron to form silver metal. Now to balance this, we'll need 2 silver ions for every copper. And so this is the balanced net reaction. Whoops, which I made a mistake. This should be plus 2 silver metals, sorry. Plus 2 silver metals. And that's your basic battery. There are shorthand ways of writing this particular battery. One shorthand way of writing this battery is by using a cell diagram. Cell diagram is a compact way of representing this. And so in a cell diagram, we write the anode on the left and the cathode on the right. At the anode, what's happening? Well, at the anode, we have copper metal going to copper 2 plus, aqueous. And then we have a double bar. And then on the right, we have silver ions going to silver metal. Here. If this is under standard conditions, then this would be at 1 molar, and this would be 1 molar, if it's under standard conditions. If it's under non-standard conditions, then you could have whatever concentrations you want here. This first bar means that there's a phase difference. The phase difference would be solid and aqueous. Phase different. Solid versus aqueous. The double bar here refers to salt bridge. And this single bar, there's a phase difference, aqueous to solid. So that would be the cell diagram for this cell. Let's show it here. So this would be the cell diagram for a different cell. In this cell, at the anode, we have zinc. Zinc is a very, very common anode. There are 2 reasons zinc is a very common anode. 1, it's easy to oxidize. 2, it's cheap. And so zinc is probably the most common anode that you find. And the anode is where we generate the electrons. It's where oxidation occurs. Anode, oxidation, generate the electrons. Those electrons are fed to the cathode. Cathode, we're going to consume the electrons. So the copper 2 is going to take the electrons to form copper metal. And so the only difference between this and the previous cell is that the anode, we have zinc in Zn2 plus solution. The anides aren't shown. You can use whatever anides you want. So we could draw this cell out if we wanted to. So this is called the schematic, but if we wanted to draw a diagram of the cell, that is not a cell diagram, but maybe a drawing or a schematic type diagram, then it would look like this. So we just put zinc solid, that's our anode. And to keep this under standard conditions, we don't need Zn2 plus here, but if we want to do this under standard conditions, then we have to put in Zn2 plus 1 molar. And let's say zinc sulfate's common, so we'd have sulfate at 1 molar too, but sulfate would be a spectator here. Okay, this is going to generate the electrons. The electrons travel left to right to the cathode. In this case, in the previous case, copper was our anode. In this case, copper is our cathode, but this is going to be an inert electrode. In the previous, we had a reactive electrode, so copper solid here. And it's going to, the inert electrode is just going to feed electrons to copper 2 ions. And this could be sulfate 2. And then we have some salt bridge. The salt bridge is whatever you want to use for the salt bridge. Could be potassium nitrate like in the previous one, or it could be sodium sulfate or potassium sulfate or whatever you want. And so what happens here is the cathode, which is the inert electrode, is feeding 2 electrons to copper 2, and it's going to plate out copper metal or deposit copper metal on the surface there. And then zinc is a great anode because it's so easy to oxidize to generate Zn2 plus and 2 electrons. And the overall net reaction here is zinc is going to be oxidized by copper ions to form Zn2 plus copper metal. And so this would be your battery here. And we could label it. This is the anode. This is the cathode here. And over here we have oxidation half. Over here we have the reduction half. Oxidation is loss. Reduction is gain of electrons. We have other reducing agents. Zinc is an excellent reducing agent, but there are other ones too. One of the other reducing agents is hydrogen gas. The hydrogen gas is a bit of a pain to work with because if you want to use hydrogen gas is not so difficult to oxidize. It's pretty easy to oxidize. What you have to do is you have to pump in hydrogen gas in here. If you want to do this under standard conditions, then you have to pump in hydrogen gas at 1 bar. So if we pump in hydrogen gas at 1 bar and then bubble it here, then we can oxidize the hydrogen. But if we oxidize the hydrogen, where do the electrons go? The electrons, they have to go to the electrode. Zinc is easy because zinc can act both as the electrode and as the reactant. Hydrogen gas is more difficult because hydrogen gas can't act as electrode. And so what we are going to do is we're going to have an inert electrode here. And so this would be the SHE anode. The SHE anode is, we're going to use platinum metal. Platinum metal is a very unreactive metal. This is, and it's not so common. This is why the old catalytic converters had platinum and palladium, which are very valuable. The price of platinum skyrocketed. And so the catalytic converters, like the old cars, for old cars, the catalytic converter is worth more than the car itself. So anyway, what you're going to do is you're going to bubble hydrogen gas, and it's going to come into contact with platinum. But platinum is not an oxidizer, is it? No, platinum is a metal. It's not an oxidizer. Where's the oxidizer? The oxidizer is attached to, well, the oxidizer is over here at the cathode. And so you need some kind of oxidizer here that's strong enough to oxidize hydrogen gas. What oxidizers are there? There are lots of oxidizers strong enough to oxidize hydrogen gas. So you have your oxidizer over here pulling the electrons, and what's going to happen is the hydrogen gas is going to get oxidized to 2H plus 2 electrons. And those 2 electrons are going to get fed over to the cathode, and the cathode is going to feed the electrons to whatever oxidizer is in solution. And so you're just going to have some oxidizer. It could be like perchlorate or whatever, chlorine, whatever you want as the oxidizer. And so here, the anode is platinum. The anode's platinum, and platinum's job is just to take the electrons, feed it into the circuit to the oxidizer. But hydrogen is the reducing agent. This is the reducing agent. And the reducing agent undergoes oxidation. So this is the oxidation half reaction here. So let's pick an oxidizer to use. Let's see if I have oxidizer here. We're going to pick copper 2 ions. Copper 2 ions are enough to oxidize the hydrogen gas. So if I put copper 2 and copper metal here, that would be a good cathode. And then the copper 2 pulls the electrons on copper. It's not going to be successful until it gets over here. It's trying to pull platinum. Platinum, it's going to be even less successful. But there's hydrogen bubbles of hydrogen gas coming into contact with the platinum. And so the electrons are going to be pulled off the hydrogen gas to form H+. Here. So does that make sense there? Now, the reason we're doing this, SAT, you know what SAT stands for? SAT stands for Standard Hydrogen Electrode. And so this would be the SHE anode. Here. And what we do is we throw on a voltmeter here. If we use copper 2 here and copper metal here, we'll throw on a voltmeter and it's going to register 0.340 volts. Now, that 0.340 volts is a composite. There's kind of a tug of war for electrons. Copper 2 wants the electrons. Hydrogen wants to keep its electrons. But copper 2 is going to overpower the hydrogen and take the electrons. And so as a result, we're going to get 0.340 volts. That 0.340 volts is this tug of war, the force involved in this tug of war. Now, that's going to be, it could be like 1 volt. Copper 2 pulls the electrons with 1 volt. But hydrogen resists. Hydrogen resists by maybe negative point. So it's resisting, it's pulling the opposite direction would be negative. It'd be negative 0.66 volts. And so if hydrogen's resisting by negative 0.66 and copper's pulling by 1 volt, then the total is going to be 0.34 volts. You see that? It's going to be a tug of war. But we don't know how much hydrogen's resisting, you know? In other words, is copper 2 ions pulling at 0.4 volts and hydrogen's resisting at 0.06 volts? We don't know. It's hard to separate. What we see is we see the sum total. We've seen this problem before. We've seen this problem before in delta H's of formation. You know, how much is due to this and how much is due to that when it's combined together. We see it for ions. And so this is what we're going to do. We're going to see that the cell voltage, which we're going to call E, electromotive force, or the cell voltage, E of the cell is equal to E of the anode plus E of the cathode. Well, I have 2 unknowns, but I only have 1 equation. If I have 2 unknowns in 1 equation, there are 2 options. 1, I could give up because I need 2 equations. Or 2, I can assume that one of them is 0, which is not correct. So what I'm going to do is I'm going to assume that the anode is 0 volts. And then this is all due to the copper. Well, I don't want to do that for everything because it would screw everything up. And so I'm only going to do this for the SHE. The SHE is defined as 0 volts. So if the SHE is defined as 0 volts, then what's going to happen is that's going to lead to a systematic error. So all the anode voltages are going to be off. You know, they're going to be too low. And all the cathode voltages are going to be too high. But what's going to happen is when you add the anode plus the cathode, one's too high, the other's too low, they cancel each other out, and it comes out perfect. Does that make sense for that? So, in other words, you can't have an anode without a cathode, vice versa. We're not ever going to be using these alone. And so it doesn't matter if I have an arbitrary 0 for one of these. And so I'll just choose this one. The SHE is defined as 0. And so the SHE anode has 0 volts. This is the anode. The anode is oxidation. And so what we say is that the oxidation potential for SHE is 0. But the SHE also has, under standard conditions, we do this. Under standard conditions, SHE has 1 bar of hydrogen. But we're forming H+. If we have H+ in here and we want to do it under standard conditions, it's got to be 1 molar, H+. Well, hydrogen is a good reducer and H+ is a good oxidizer. It's not good enough to oxidize copper. H+ will not oxidize copper metal. So electrons are only going to flow one way here. But H+ is good enough to oxidize other metals, like zinc. Zinc is a very easy to oxidize metal. Here. And zinc is a very common anode. So this is not written towards convention. This is written reverse of convention because anodes we usually write on the left. Okay, but if we put the anode on the right here, and then H+ is a powerful enough oxidizer to oxidize zinc, this will be the SHE cathode. H+ tries to pull electrons off platinum, unsuccessful. H+ tries to pull electrons off copper wire, unsuccessful. H+ tries to pull electrons off zinc, successful. So H+ is going to oxidize the zinc to Zn2+, but the electrons are going to flow backwards. And the electrons are flowing backwards here. If we have our voltmeter connected in a normal way, it's going to register a negative voltage. And so what that means is this. E of the cell for this is equal to the anode plus the cathode potential. And when I add these two up, I don't know which one's which, and so I'll call this one 0 volts, and then that means that the potential, the oxidation potential for zinc is going to be negative. Negative, what does that mean? Well, a negative just means weaker than hydrogen, or H+. And so let's take a look at these. So you don't really have to worry too much about these, but these are all reduction half reactions here. And these are all reduction potentials. Yeah. And so these would all happen at the cathode. And so if I look at the reduction potentials here, and I look at H+, H+ has a reduction potential of 0 volts by definition. So if it has a positive reduction potential, it means it's stronger than H+. If it has a negative reduction potential, it means it's weaker than H+. It doesn't mean that things reverse. It just means that it's weaker than H+. And so the higher the reduction potential, the stronger the oxidizing agent, and the more likely the reduction reactions to occur. The smaller the reduction potential, the weaker the oxidizing agent. Now, these are reduction potentials. If I flip the reaction backwards, it would be the oxidation potential. So if I flip the reaction backwards, then I change the sign on all these. So what species has the highest reduction potential on the chart? What species has the highest reduction potential on the chart? Fluorine. What is the reduction potential? Plus 2.866 volts. So fluorine's the strongest oxidizer on the chart at plus 2.866 volts. What's the weakest oxidizer on the chart? The weakest oxidizer on the chart is lithium ions. Lithium ions have a negative 3.05 volts. That's 6 volt difference in reduction potential. So in other words, fluorine gas is 6 volts higher in potential than lithium ions. So fluorine's significantly stronger. All of them are oxidizers, whether it's negative or positive. And again, it's just arbitrary. These negatives don't mean that it's a reverse reaction. The negatives just mean it's weaker than hydrogen. Right? So once we do this, once we have the SHE, then we can determine the cell potential very easily. So let's see how this is done. We don't have to have the SHE. We just have the SHE just to get the table. Once we get the table, then we can use all the voltages. And so the next thing that we do is we calculate the cell voltage. And calculating the cell voltage, we can use one of two equations. I don't like this equation here myself. I like this equation here. E of the cell is equal to E naught, this is under standard conditions here, of the anode, where we generate the electrons, plus E naught of the cathode, where we consume the electrons. So what's the anode here? The anode is zinc goes to Zn2 plus. And so what we can do is we can do this using cell diagram shorthand. Zinc solid goes to Zn2 plus. This is how I read that. So zinc solid goes to Zn2 plus. What's the voltage? So I go to the chart. Zinc is a really good reducing agent, or is easily oxidized as a good reducing agent. So we go from zinc to Zn2 plus. That's the reverse of this. So if we go in the reverse direction, we change the sign. And so it's plus 0.763 volts. So we reverse that, so that's plus 0.763 volts, because it's backwards. So that reaction, Zn2 plus goes to Zn. Plus the cathode. What was the cathode? And this one was copper, right? Okay. And so the cathode was copper 2 plus goes to copper solid. And so let's take a look at the voltage for that. It would be here. Copper 2 plus goes to copper solid. It's not there. It's up there. And that's plus 0.34 volts. So we can just use it as written. So this is plus 0.340 volts. So altogether, we're going to get 1.103 volts. Yeah, 1.103 volts. What your book does is they use the reduction potentials as is. So here, you can't have reduction and reduction. As copper 2 gains electrons to form copper metal, zinc 2 gains electrons to form zinc metal. One of these has to be reversed. And so what they did was they used a negative sign to flip it over. So I don't like this equation because we should just use the cathode potential plus the anode potential. The higher the potential, the more strongly driven the reaction is. And so it's always the same. And so some people start thinking backwards. You know, they think lower the potential is better. No, we want the higher. And so if both of these are high, then the cell potential is going to be high. So I don't like this equation myself, but if you like it, I don't care if you use it or not. So this is our for standard cell potential. standard cell potential is related to the driving force. The higher the voltage, the greater the driving force there is. And the relationship to the driving force, delta G, is pretty straightforward. Delta G under standard conditions is equal to minus NFE under standard conditions. And this is the cell potential under standard conditions. So N is the number of electrons, number of moles of electrons transferred in the balanced net reaction. F is the Faraday constant. The Faraday constant is depends on how many sig figs you want it. The Faraday constant is 96,485 coulombs per mole of electrons. Coulomb is the unit of charge for electrons. Let's see if I have that here. No. And E is just the cell potential. And, in volts, which is Faraday's there. So the units are going to be the Faraday Coulomb. Coulomb times a volt is a joule. And so we'll get joules per mole. So Coulomb times a volt is equal to a joule. Right, so this is the relationship between E naught of the cell and the driving force. But we have a bunch of other relationships. Thermodynamics is full of these relationships that we can generate. So if we can relate it to delta G, we can also relate it to K, because we know from earlier that delta G naught is equal to, what is it equal to? Yeah, it's equal to delta G naught is equal to delta H naught minus T delta S naught, which is also equal to minus RT ln of K, right, when delta G under non-standard conditions. Which means that this is equal to minus NFE, naught of the cell, which means that K, or E naught of the cell, E naught of the cell is equal to RT over NF, RT over NF, ln of K. So if we know the equilibrium constant and we know the temperature, then we can figure out what the cell voltage should be. Or we can figure out what K is. K is going to equal, what would that equal? That would equal E to the E naught of the cell over RT NF, something of that sort, etc. So we can use this to calculate other things as well. Yeah. Etc. So let's look at some thermodynamic calculations, a typical one. So if we just look at a typical reaction here, zinc plus copper 2 plus goes to Zn2 plus Cu2 plus. What we're going to have is this. What's that?
Sorry, do you mean copper solid or?
Oh, yeah, sorry, copper solid. What we're going to have is, okay, we can figure out what delta G of this is for this reaction. Delta G, we're just going to use the delta G's of formation. So if we look at the sum of the delta G's of formation of the product minus the sum of the delta G's of formation of the reactant, then we'll get our delta G value here. And then from that delta G value, we can figure out the cell potential. The cell potential is just going to equal our delta G value over, what is it? NF. So minus delta G over NF. Now, it's kind of one thing that's kind of different between cell and delta G is this. They're similar because they tell us the driving force, right? And so in other words, if delta G is very negative, that's a strong driving force. That's going to mean E, the cell, is very positive. So if delta G is much less than 0, that means E, the cell, is much greater than 0. Because delta G's are negative, that E, the cell, is going to be positive because this negative is going to change the sign here. But they're different in the sense that delta G is extensive and depends on the amount. Whereas E naught of the cell is intensive. It doesn't really depend on the amount. So, in other words, the amount of energy or the amount of work that you can do depends on how much methane you combust. So if you combust 2 moles of methane versus 1 mole of methane, you'll get twice as much energy with 2 moles of methane, right? 3 moles of methane, you'll get 3 times as much energy. But will we get 3 times as much voltage? So methane, if we make a methane, you can make a methane battery. You know, methane is a good reducing agent. Oxygen is a good oxidizer. You can make a methane battery. So if we make a methane battery, if we have 3 times as much methane, are we going to get 3 times the voltage? No, we're going to get 3 times the work, but we're not going to get 3 times the voltage. The voltage is going to be the same. And so this is like, you know, if you have let's say if I have a AA battery versus a quadruple A battery, and quadruple A batteries are tiny. Have you seen those? Quadruple A battery is tiny, AA battery is like twice as big. So if a AA battery is twice as big, is it going to give you twice the voltage? The answer is no. It doesn't give you twice the voltage. It's going to give you the same voltage. It's just going to last twice as long. And so the situation is like this. If I have 1 gallon of 6 molar HCl versus 2 gallons of 6 molar HCl, is 2 gallons twice as reactive? Is it going to give you twice the voltage? No. 2 gallons is going to last twice as long. That's it. It's going to give you the same. And so in that sense, they're different. Whereas delta G is going to tell you the amount of work that you can do. Well, you can do twice as much work with 2 gallons of HCl versus 1 gallon of HCl. And so it's extensive versus intensive there. So when we do this, let's take a look at like zinc. Solid goes to Zn2 plus 2 electrons. And we look at the cell potential for this. Oh, this is not cell. This is going to be oxidation potential. We look at the oxidation potential for this, and it's going to come out to however many volts. So that's zinc solid goes to Zn2 plus. So zinc solid goes to Zn2 plus, which is backwards, therefore we have to change the sign, so it's plus 0.763 volts. So this is 0.763 volts plus. Your book would have us do this. From the book would say that the oxidation potential for this is equal to the negative of the reduction potential. of this. And so the reduction potential is negative 0.763 volts, and then you times it by negative to get the oxidation potential. And so this is why I don't do it this way. Okay, what if I did this? What if I did twice as... So rather than 1 mole of zinc, I go 2 moles of zinc. If I did 2 moles of zinc, I'm going to get 2 moles of Zn2 plus 4 electrons, 4 moles of electrons. What would the oxidation potential for this be? Would the oxidation potential for this be double? No, the oxidation potential is going to be the same, plus 0.763 volts. What about the delta G's? Would the delta G's for these two be the same? No, the delta G's didn't tell us the amount of energy, and they're going to be different. The other thing is, did the concentration change? The concentration, under standard conditions, this is 1 molar. Under standard conditions, this is also 1 molar. And so the potential doesn't change. There. The delta G's are different. So delta G for the second one's 2 times delta G for the first one. But, you know, delta G, it's also per mole, you know, so we can normalize it too. We can make delta G intensive. The way we make delta G intensive is we use these units, kilojoules per mole. So it's always the same, kilojoules per mole. Versus kilojoules. That, when we use kilojoules, we're making it extensive. That is, depends on the amount. So we can do different calculations, you know, acids and metals, the calculation I was looking at here. So if I have acid, here, H plus, goes to H2, what's the reduction potential for that? This is 0 volts. What can I oxidize? Well, what can I oxidize? For oxidation, I have to reverse these. So for lead, I would reverse it. So will H plus oxidize lead? So if I reverse this equation, that converts it to plus 0.125 volts. So that's 0 plus 0.125 gives us a positive voltage. A positive voltage means there's driving force. And so what I can oxidize is anything with a positive oxidation potential, which all these would be when I reverse it. However, if I reverse this one, let's say, will H plus oxidize copper metal? Well, in order to oxidize copper metal, I have to reverse this one that goes negative. So I got 0 volts minus or plus a minus 0.3 volts. That's going to give me a negative cell potential. The negative cell potential means that there's no driving force. And so what we can do is we can easily see what's favorable and what's not favorable by seeing if they add up to a positive cell potential, then there's driving force. If they add up to a negative cell potential, there's no driving force. And so the cell potential has an absolute 0. So if E of the cell is equal to 0 volts, that means something. That means the battery's dead. If E of the cell is greater than 0 volts, that means the battery still has life. You know, so it's a live battery. If it's less than 0 volts, then there's no driving force. Reverse reaction is favored. Maybe you hooked up the voltmeter wrong. However, when we're looking at anode potentials, an anode potential greater than 0 means what? It means stronger than hydrogen, H2. An anode potential of 0 volts means we're hydrogen by definition. An anode potential of less than 0 volts means weaker than H2. H2 being your reference reducing agent. Cathode, the reference oxidizing agent, is H+. So if the cathode potential is greater than 0 volts, that means it's stronger than H+, our reference. If it's equal to 0 volts, that means it's H+. And if it's less than 0 volts, it means it's weaker than H+ as the oxidizer. And so these are arbitrary. The half potentials have an arbitrary 0. But that arbitrary 0 cancels out when we look at the cell potential. Because this is an absolute 0. This is an arbitrary 0. Yeah. And so the zeros mean two totally different things. When we're looking at half potentials, the 0 means one thing. When we're looking at a cell potential, the zeros mean totally different thing. Because remember, the two systematic errors cancel one another out when we do the cell potential, because the cell potential is the combination. The cell potential is the combination of the anode potential plus the cathode potential. The higher the anode and the higher the cathode, the higher the cell potential. That's simple compared to the book. The book would go the higher the cathode potential and the lower the anode potential, reversed, would be the higher cell potential. Okay. Let's see. What if we're under non-standard conditions? Well, if we're under non-standard conditions, then we use the Nernst equation for non-standard conditions. That is, the Nernst equation can be derived from delta G under non-standard conditions is equal to delta G under standard conditions plus RT ln of Q. Delta G under non-standard conditions is equal to minus NFE of the cell under non-standard conditions. Delta G under standard conditions is equal to minus NFE of the cell under standard conditions plus RT ln of Q. Then we're going to divide both sides by negative NF. If we divide both sides by negative NF, then we get this equation. E of the cell is equal to E naught of the cell minus RT over NF ln of Q. Now, the next step is we're going to convert to base 10, log base 10, by multiplying by 2.303. And so E of the cell is equal to E naught of the cell minus 2.303 RT over NF log base 10 of Q. What is the most common temperature we use? 298. So what we're going to do is we're going to assume 298 Kelvin. Assume T equals 298 Kelvin. If we assume that the temperature is 298 Kelvin, then we're going to multiply R is a constant, T is a constant, F is a constant. And so what we're going to end up with is E of the cell is equal to E naught of the cell minus 0.0592 volts over Z. We're going to call N Z. I don't know why. But we're going to, instead of calling that N, we're going to call it Z, which is the number of moles of electrons transferred in the balanced redox reaction.
This is it like delta Z?
No, just Z. Z and N are the same thing. A lot of books will leave it N rather than changing it to Z. Okay, so that's the Nernst equation. And what happens here is this. As the reaction progresses, the reactant concentration goes down, the product concentration goes up, so the voltage goes down. And so what the Nernst equation predicts is the voltage is going to go down as the reaction progresses. So when you have a new battery, it starts off here. And as you start using that battery, it just starts declining. Actually, if you have a new battery under standard conditions, it starts here. And then the voltage just declines from there. And so this would be a new battery under standard conditions. If you want to go non-standard, you could add more reactant, higher concentration of copper 2 plus. And as the concentrations change, the driving force changes and the voltage changes. So we can do it this way. This is weird initially. So platinum is inert electrode. And so the reducing agent's iron 2. Iron 2 is going to be oxidized to iron 3. In the process of going from iron 2 to iron 3, we're going to lose one electron. That one electron is going to be fed to platinum. Platinum is going to feed the electron over to the cathode. The cathode is silver. Silver is going to feed the electrons to silver ions. So that's what's happening here. And so we have an inert electrode here and an inert electrode here. We have to use an inert electrode here because iron 2 plus is not a good material for electrode. It's just aqueous ions. Now, when the phase is the same, we use a comma to separate. So this is reactant product in the anode beaker. This is reactant product in the cathode beaker. And so when we draw the cell is going to look like this. So we put in our inert platinum electrode here. Platinum is a very common choice for inert electrodes. And then what we have here is iron 2. Iron 2 is going to be oxidized to iron 3. In the process of oxidation, it's going to give up an electron here. The electron is going to be fed over to the cathode. Now the cathode is going to have an inert electrode, silver, and that is going to feed the electron to silver ion. Silver ion is going to pick up that electron that comes in over here to deposit silver metal on the surface of this electrode here. And so if we deposit silver on silver, then it stays nice and clean. Yeah. So under standard conditions, this is what we have to have. Under standard conditions, we need iron 2 at 1 molar. We need iron 3 at 1 molar, and we need silver ions at 1 molar. Then everything's under standard conditions. If it's under standard conditions, then we can calculate the cell potential. The cell potential is the anode potential. The anode is where oxidation occurs. And the oxidation is iron 2 gets oxidized to iron 3. We use a comma here instead of a bar. Plus the cathode potential. The cathode potential is just silver ion takes an electron to deposit silver metal. And so let's calculate the standard cell potential for this by looking up the values in the chart. So iron 2 and iron 3, I'm going to find those. So the first one I look for is iron 2 goes to iron 3, so that's backwards here. Iron 2 goes to iron 3 means I have to reverse this one. And if we reverse it, it's going to be plus 0.771 volts. Oh, sorry, minus 0.771 volts. So this is minus 0.771 volts because I had to reverse it. Then I have silver ions go to silver metal. That's plus 0.800 volts. So this is going to be plus 8.800 volts. And so this is going to give me plus 0.029 volts. And so it's not the highest potential, but we have a driving force for this reaction to occur as long as we need a salt bridge in here. If there's no salt bridge, nothing's going to happen. So the salt bridge could be like sodium nitrate, etc. The nitrates would go to the anode, which is over here, and the sodiums would go to the cathode, which is over here. So cations to the cathode. Right, but what happens if I change these concentrations? If I change these concentrations, then it's going to change the voltage. So I need to look at the net reaction here. The net reaction is iron 2 gets oxidized by silver ions to form iron 3 and silver metal. So the iron 2 is at 0.10 molar. So this is 0.10 molar. The silver ion is at 1.0 molar. The iron 3 is at 0.20 molar. And so the silver is pure solid. And so Q is going to equal the iron 3 concentration divided by the iron 2 concentration and the silver ion concentration. So that's going to equal 0.20 divided by 0.1 times 1, which would just be 0.10, which is going to give us 2.0, 0.2 over 0.1. So that's my Q. And then I'll just plug it into the Nernst equation here to calculate the new voltage. And so the Nernst equation says E of the cell under non-standard conditions is equal to E of the cell under standard conditions minus 0.0592 volts over Z times the log of Q. Okay, so we calculated the cell potential under standard conditions as 0.029 volts minus 0.0592 volts divided by Z. Z is the number of electrons transferred in the balance. And so how many electrons are transferred here? Just one. So iron goes to iron 3 plus an electron. And then silver ion picks up that electron to go to silver. So just one electron. So Z is 1. And then the log, we calculated what Q is. It's log of 2. I expect the voltage to go down. The reason I expect the voltage to go down is because the product concentration is higher than the reacting concentration for iron 2. So log of 2 is 0.693. Or I'll just do it. No, that's not 0.69. ln of 2. Log of 2 is 3.3 times negative 0.0592 equals plus 0.029. 0.011. So the voltage has gone down 0.011179 volts. Go up 0.011 volts. under non-standard conditions. All right. Let's do this. Let's check out. We're going to check out model kit today. I'm going to stop here for this electrochem. We're going to check out a model kit from the stock room, and we're going to build the trioxylatochromate ion structure. But do you know that there are two structures for trioxylatochromate? We're going to build both of them and see what the difference is. And so let's try that now. There's a left-hand form and a right-hand form. You know, these are called optical isomers. So the best way to see it is just to build it. Let's see. So I'm going to just have you build it and try to build two different ones. You know they're different when you can't superimpose them. If you can superimpose them, that is, you can rotate one and it matches the other, then the same structure. So try to build two different structures for trioxylatochromate.
She's ready for us?
Let's go take a